Before I start writing formulas and concepts, maybe a few words of introduction. Kolmogorov statistics is an old topic. Most distributions connected to that are known. But I will show you a different approach. I will use point processes to derive distributions of Kolmogorov statistics. It's perhaps not cutting-edge research, but it is fun, and it gives you an insight in how these distributions that are used often in statistics to check whether two samples come from the same distributions are derived. And I will now try to share the other screen and draw a few pictures for you. So here is a picture for starters. We all know about Poisson processes. Poisson processes are a bunch of points in the plane. And what you require is that the number of points in every fixed set has a Poisson distribution with a certain parameter. And if you take disjoint sets, then the number of points in disjoint sets are independent Poisson random variables. The idea that I will use today, and it's an old and well-known idea, is that if you toss a coin for every point that you see in the Poisson process independently, and you say, this is heads, this is heads, this is tails, this is heads, tails, tails, heads. And then if you erase all the points where you got tails, which means you erase this point, and this point, and perhaps this point, what is left is a Poisson process. This idea is called thinning. And it's not very difficult to prove. It's an elementary computation that you have to do, and it's a well-known result. It's been around for many, many years. And even more is true, that if you do, if I put back the points where I got tails, so I will now replace the points. Here I got tails, 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 tails. Then you get two distinct processes. So you get, if I paint the points where I got an H with red, I get this process. And if I paint the other ones blue, I get this process. And these two are distinct Poisson processes, and one nice thing is that these two Poisson processes, the blue one and the red one, are actually independent. Again, this is an old result. It's been around for a long time. And we can go even further with this idea. This then leads to the idea of marked point processes, because you're attaching marks to the points of the original Poisson process, and you can do other things. You can, for example, do this. Instead of saying heads and tails, you can roll a die, and you say, here I get a 1, here I get a 6, a 5, a 4, and 4, and 3, and perhaps here I get a 2, and a 1. Then again, you have marked every point in the Poisson point process with a label. When we tossed the coin, the labels were heads and tails. Here the labels are 1, 2, 3, 4, 5, 6. And if you then look at all the processes that you get, the process that carries the label 1 is again a Poisson process, which is more or less obvious from the coin tossing example. The process that carries label 2 is again a Poisson process, all the way up to the process that carries the label 6. And they're independent Poisson processes. So again, you can sort of separate a Poisson process into several independent Poisson processes by marking them. And the important thing here is that the marks are independent. So you independently roll a die for every point in this Poisson process. And you can go even further. You can make it location dependent, which means that what you do is you say, I will not roll the same die for every point, but I will choose a different die with different probabilities for every point. And you can make the probabilities location dependent. So if you see a point here, the probabilities on the die will be such and such. If you see a point here, the probabilities on the die will be different. So the dice that you roll can be different dice depending on the location, which means that the probabilities for labels 1 to 6 depend on where you are in space. And again, what you do is the labels separate the original Poisson process into labeled Poisson processes, and they are independent Poisson processes. And not too hard calculation lets you compute the intensity of these Poisson processes. If you always roll a fair die, then the intensity of these separated Poisson processes, it's just 1/6 of the original intensity. If you make it location dependent, then the new intensity is given by an integral. We'll see that later. But the important thing to remember is the simple fact that if you mark a Poisson process with different labels, that gives you a bunch of independent Poisson processes. You can think sometimes this is phrased in a way that you paint the points of a Poisson processes where you choose paints independently, and the selection, the probability of different selections can be location dependent. But the very simple underlying idea is that the new processes, point processes that you create that way, are independent Poisson processes. And this example is totally abstract. You can imagine in this picture, the points are in the plane, but they can be in principle in any abstract space. So these can be points of a Poisson process in any abstract space, and all the arguments are still valid, right? As long as you attach labels to the points of a Poisson process independently for each point, then the labeled processes, then you separate. If you collect all the points that belong to one label, then you separate the Poisson process into several independent Poisson processes. You can make it location dependent, as I said before. The argument is still valid. You still get independent Poisson processes, but the intensities are somewhat more difficult to compute, but not that difficult. I'll show you the form of formulas in a little while. Now, my next idea, the next thing that we will use today to derive the distribution of the Kolmogorov statistics has to do with Brownian motion. And you have all seen this picture that Brownian motion looks like this. It starts at 0 and then it moves randomly. It's a very well-known picture of Brownian motion. And if you look at this picture, you say, yes, Brownian motion is a stochastic process. We know that it's a Markov process, a Levy process. It has many nice properties. It's one of the stochastic processes that has been most thoroughly researched in the past. But it doesn't seem that it has to do with point processes. There are no point processes. There are no obvious point processes here in this picture. But the Japanese-American mathematician Kiyoshi Ito, back in the 60s had a brilliant idea and connected Brownian motion with Poisson processes. He said that you can split the path of the Brownian motion into excursions. Like one, that means that you have pieces of the path of Brownian motion away from zero. Like I can say this is one excursion, here it is at zero, then it goes away and does its thing, and then it returns to zero. And this piece of the Brownian path is called an excursion away from zero. And these excursions can be positive or negative. And what you can do now is you can split the entire path into these little excursions away from zero. And you will get a picture like that. So you have here a small excursion, then you have the next one looks like this. Then you have this one. And the next one looks like this. Then this big one that I drew before. And you get little pieces of functions. And one of the brilliant ideas of Kiyoshi Ito was that you can see these pieces of functions as a Poisson process in an abstract space. It's a function space, but Poisson processes can be fairly general. They're just points in an abstract mathematical space, which can also be a function space. And one more idea that makes this entire story tick is that you can choose labels within these excursions that have the property that the label of an excursion that comes later is bigger than the label of an excursion that came earlier, and all the labels are different. And you can interpret these labels as local time. That means that you can devise, you can measure time in such a way that you, in a way you know when an excursion occurred. So in the end, the Poisson process will look like this. So you will have an abstract space that now will be called U. It's a function space. Here you will measure the local time. And every now and then you will have an excursion that has that local time. For example, at this local time, let's say L, an excursion occurred and it looked like this. And if you take the pair of the excursion, this excursion is then called E of S. Sorry, it's called E of L because it occurred at time L. E of L. And if you take the pairs, the local times when the excursion appears and the excursion itself, then this pair is a Poisson process. It's a two-dimensional Poisson process, an abstract one. I admit it's a point process in a very abstract space. It's a function space. It's a space that contains functions, but it can all be made mathematically rigorous. And you can compute the intensity of this Poisson process, and it's the product, it's a Cartesian product of the Lebesgue measure and a measure that's called Ito measure that sits on this function space. But this is all very abstract, but in the end, it's nothing but a Poisson process. And if we go back one slide, we said that if you mark a Poisson process, then you can you separate the Poisson process into several components that are independent into several Poisson processes. And then if you have this abstract Poisson process, which consists of excursions that are coming at certain times, right? These times are a discrete, but a discrete set of times. Every now and then you get an excursion. You can again mark this Poisson process. It doesn't matter that it's very abstract. The idea is as simple as the original idea. You take a Poisson process, you attach marks, you either toss coins, independently, or you toss, or you roll a die independently, or you take more complicated marks. As long as these marks are independent of each other, so you mark every point independently of each other, then the mark process will be again a Poisson process. And this is also true here. And the idea how to mark the excursion of a Poisson, the excursions of a Poisson process is the following. And it again recycles the idea of a Poisson process, but this time a very simple one. When you have courses in probability at the introductory level, then you talk about Poisson processes on a line. And sometimes you call them counting processes. And you then argue that the simple Poisson process on the line is the only process with independent stationary increments. And what we do here in this particular case, I will take an independent Poisson process. I will choose another color, say green, and then I will run a Poisson process on the time axis of the Brownian motion, and I will get a point of the Poisson process every now and then, right? So I will get a bunch of green points, and there I will choose them, this Poisson process of green points, to be independent of Brownian motion. We can always choose the process in such a way, or construct the process in such a way that it's independent of the Brownian motion. And now the main idea of this entire presentation is that you say, I will consider that excursions that contain a green point are marked. So it's like tossing a coin. I will say, if the excursion contains a green point, I will consider that I got heads on my coin, and I will consider that excursion to be marked. And the properties of usual Poisson processes on the line guarantee that because the green Poisson process is independent of Brownian motion, the marks are attached independently. So if you only take excursions that contain a green point and ignore the other ones, then you will get a new Poisson process of marked excursions. And in this particular case, it would look like this, right? I erase all this, I erase this excursion, and then I erase this excursion here, and then I'm left with a new sequence of excursions. You know that every excursion comes at a given time. You can construct the so-called local time in such a way that we have a clock that measures when an excursion occurred. And then the excursions containing a green point are a Poisson process. Again, this looks very abstract because we're dealing with functions, we're dealing with Poisson processes that have their values in an abstract space. But the underlying idea is the same, and the proof that the new process is a Poisson process is just the same as in the elementary case. And we know how to compute the intensity of this new Poisson process. And this will be the Poisson processes that I will use in my presentation. So if I say it again, right, you can attach to every excursion a time when it occurs, called the local time. You know that the local time of an excursion that comes later is bigger than the local time of an excursion that comes earlier. And if you do your local time right, then the process of excursions is a Poisson process. This is Ito's brilliant idea. It makes many calculations possible. And at the beginning, Andrea was mentioning that yesterday's speaker was mentioning the Pittman-Muir process. This idea is below that, is underneath that process. This is an idea that I use in my dissertation to derive the first proto version of what is now called the pit-manure process. Okay, let's now go to formal definitions. I don't think I need to explain to you what the Kolmogorov statistics is. From the theory of empirical processes, you know that in the right way it converges to the Brownian bridge. And then the asymptotic distribution of the Kolmogorov statistics is derived from the maximum of the absolute value of Brownian bridge. But let's now go to the more formal part of my talk. And I'll need to make sure that I stop. I will switch to the more formal definitions. Here is what I will say in my talk today. I already explained what marking Poisson processes means. Space-dependent marking, that means that we can choose a die in every point of the space, and it can be a different die. I explained to you what marking excursions of Brownian motion by an independent Poisson process. It's the same idea, and that the marks are attached independently, again, depends on the simple property of Poisson processes, that if you look at the number of points in these joint sets, you get independent Poisson random variables. And I will then tell you in what way this idea of marking Poisson point processes is related to Kolmogorov statistics. It seems to be rather unrelated at the beginning, but in the end we will see that it makes possible a rather elegant and straightforward derivation of the distribution of the Kolmogorov-Smirnov statistics and many other statistics. Okay, so here are the formal definition. If you have a general Poisson process on a space, we can mark points by attaching to a point of this Poisson process a label y from another abstract space. And the resulting point process in this Cartesian product turns out to be a Poisson process, provided the labels are attached independently. That means that for every point in the Poisson process, we toss a coin independently of all the other points. And it doesn't come as a surprise that the measure of this new process, this new labeled process, is the Cartesian product. Here we have a case where the probability of marks or labels that are now abstract labels, they're not 1 to 6, but you can imagine that you can attach all sorts of labels. You can attach a real number to a point of a Poisson process and call it a label, or you can attach an integer, positive or negative, to a point and call it a label. So labels can be very general. If we make it space-dependent, which means that we choose a die depending on where the point is in the plane, then that means mathematically that for every point x in the plane or in an abstract space, we have a measure for labels. We have the same set of labels, but the distribution of these labels that we choose independently for every point in the Poisson process depends on x. So in one point you choose this die, in another point you choose that die, but you roll them independently, and you get the joint labeled Poisson processes, and that labeled point process is again a Poisson process, and this integral gives you then the intensity of that new labeled Poisson process that lives on the Cartesian product of the space where the original Poisson process lives and the space where you choose labels. Okay, Here we return to the discussion about the Brownian excursions. It all looks very abstract, but in the end, it boils down to a simple Poisson process, right? I admit the ethos idea was brilliant to see the excursions as point of a Poisson process in an abstract space. It's an absolutely brilliant idea. But in the end, it reduces to the simple notion of a Poisson process. It's nothing more, except that the space where these Poisson processes live are much more complicated. And the way we label excursions, as I showed you before, is that we consider the excursions that are marked, the excursions that contain a green point, as labeled. And because the Poisson process, which we use to label the points, is independent of Brownian motion, the probability that an excursion is marked depends on its length, right? And the number of points in that green Poisson process is a Poisson random variable in any excursion, and it is marked if the number of green points is 1 or more, which means 1 minus the probability that we have no green points in that excursion, which, because of independence, means that we have no points in a given fixed interval, no points of a very usual Poisson process in a given fixed interval. And if we now separate the marked and unmarked excursion, the theory of Poisson processes tells you that those are two independent Poisson processes. And we will use that fact later on. And let's continue. We know what the probability of marks is, and what I will use is yet another property of Poisson processes, which is that if you map a Poisson process by a function, then the result is still a Poisson process. Like, for example, if you have points in the plane that are a Poisson process and you take only the x-coordinate, the x-coordinates are again a Poisson processes. So that maps of a Poisson process give you a Poisson process is very easy to prove. Much easier to prove than to prove that marked Poisson processes are independent and to derive the intensity of those Poisson processes. Now, the theory of Brownian motion tells you the probability that the excursion, the length of an excursion, is bigger than r. That is one projection. The length of the excursions are a projection from the big space, big abstract space of excursions. So what you say is, for every excursion, I know that the pair local time and an excursion is a Poisson process, but then from that pair, I only take the length of the excursion. And that's a map, that's a function. So you attach a value, a function attaches a value to every point in the Poisson processes. So you take an excursion, but then you say, I'm only interested in the length of that excursion. And you know that the length of the excursions are a Poisson process, because all maps of Poisson processes are Poisson processes. And you can derive the intensity of that Poisson process, which is given here. So from this, intuitively, what you can infer is that there will be very many very small excursions and a few very big excursions in Brownian motion, which is somehow intuitively clear. And a routine calculation gives the probability that an excursion is marked. You just have to compute this integral. It's called the Frullani integral. It takes a bit of a Fubini theorem to compute it. It's not very hard, and this is the result. So if I now go on, I told you that there is a way to measure time for excursions. So every excursion occurs at a given time. It's not the normal time. You have to devise a way to measure time in the right way, and then it becomes local time. And the properties of the Poisson processes again give you one simple fact. You know that if you take a very simple Poisson process on the positive real line, then the distribution, then the distance of the first point from the origin is an exponential random variable. That's a very elementary fact. You do that, you compute that in elementary probability courses. But again, that is true for any abstract Poisson processes. So if you have points coming in at certain time, the occurrence of the first point will be at an exponential time. And if you measure time as local time, then the local time at the time when you get the first marked excursion will have exponential distribution. So now things are slowly coming together, right? I'm using very simple facts. I'm using elementary facts. If you have a Poisson process and a positive real line, and if you look at the distance of the first point from the origin, that distance will be an exponential random variable. And we can compute the distribution of that random variable using Itoth excursion theory. And here's now the picture that will be the basis where we will connect Poisson processes, and we will connect Brownian motion and Brownian bridge. I will be running Brownian motion. This is a picture. It's supposed to be Brownian motion. It is simulated on the computer. And what I will do is I will stop the Brownian motion at an exponential time that I will call S theta. S theta is an exponential random variable. And in the pictures that I showed you before, this S theta would be the first green point. Right? We took the path of the Brownian motion and we ran in parallel a green Poisson process, and there was a first green point somewhere. But we know that the first green point comes at an exponential time. And I will denote that exponential time, the time of the first green point, by this S theta. And this excursion that starts here at the last time before S theta, when Brownian motion was 0, this part is part of the first marked excursion. And what comes before are unmarked excursions. So they didn't contain any green points, so they're unmarked. And we know that marked and unmarked excursions are two independent Poisson processes. And one more idea that I will write down formally a little later is that if you look at the path of Brownian motion up to this time g theta, it starts at 0, it ends at 0. It looks very much like a Brownian motion, a Brownian bridge, because, you know, Brownian bridge starts and ends at 0. And it is, of course, it isn't a Brownian bridge. It's a Brownian bridge that's been rescaled by an independent random variable. That goes back to an old result by Dinkin. He says that if you take this portion of Brownian motion up to here, and if you do Brownian scaling, so that you scale it back to the interval between 0 and 1, and you use the square root for the space dimension, then you get a Brownian motion, then you get a Brownian bridge. So what this is, and that Brownian bridge is actually independent of g theta. So what you see here is that this part of the path of Brownian motion, this piece of path of Brownian motion is just Brownian bridge that you have stretched for a random amount that you call g theta, and you have stretched by the square root of g theta in the space dimension. So you can think about this as a randomly rescaled Brownian bridge. But this Brownian bridge has excursions, and every excursion has a height. Like this excursion here has this particular height. And we know that this excursion here has a particular local time. But we're looking at functions of Poisson processes. These unmarked excursions are flying in as points of a Poisson processes, as point of a Poisson process. It's an abstract Poisson process. The simple undergraduate Poisson process is you're looking at time, and then every now and then you have a point on the real line. If you have a more abstract space, you're looking at time, and every now and then you have a point in an abstract space. But it's still, the underlying concepts are all the same. It's a Poisson process. So if you take the map of this Poisson process of unmarked excursions that gives you the height of every excursion, you will get a Poisson process. And here is the connection. But if you know the heights of all the excursions, if I know the height of this excursion, which is negative, and the height of this excursion, which is positive, if I know the Poisson process of all these heights, then I will know the maximum of this piece of path up to g theta, right? To determine what the maximum is of the absolute value of this piece of path up to g theta, I just need to know the heights of the excursions. So I will take the absolute value of every height, and I will see which one is the largest one, and that will be the maximum. And that maximum is just the rescaled Kolmogorov statistics. I will maybe show you a clearer picture a little later, but let's go on with our slides. Hold on, I need to erase this. So here are some formal definitions that we need to formulate. So if S is exponential with rate theta, and then if g theta is the supremum of all the times before this random time, before this random exponential time, when b theta was at 0, then what we know is that that piece of path up to the last time before the last 0, so if we go back to the picture, what I'm looking at the piece of the Brownian path all the way up to g theta. This is what I'm interested in. And if I rescale this, which means if I do this and then s goes from 0 to 1, I should have a 1 here, sorry. Then this process, this new process that we get is Brownian bridge, and it's independent of g theta, and it's independent of s theta. This is what you get from this result by Dinkin and from properties of Brownian motion. And now we're close. Now we're close to getting somewhere with this connection between Poisson processes and Kolmogorov statistic. And I believe I need to speed up a bit. And one more thing that I should mention is this. If we return to this picture, we know that the excursions that are coming in time, the local time, are a Poisson process. And the unmarked excursions are a Poisson process, and we know how to compute the intensity of that Poisson process, at least in principle. And we know that this piece here of the Brownian path up to g theta is just a rescaled Brownian bridge. And if we know the local time at g theta, then we know that this piece of path decomposes into excursions that are a Poisson process up to a certain time. And here is now a more formal statement of the idea. This is just a statement of what Dynkin says. And if you put these two facts together, the simple fact that the first point in the usual undergraduate Poisson process is at an exponential distance from the origin, that's one thing that we're using in an abstract setting. And conditionally on the local time, the excursions of Brownian motion up to G3 are a Poisson process. So I have another picture here that will try to explain. Now, first I need some notation, right? If U is the standard Brownian bridge, we can look at the maximum of on the positive side and the minimum of the Brownian bridge, which is and multiplied by a minus, so that both these random variables are positive. And Dynkin tells us one more thing. If we go briefly back to the picture, this is an exponential random variable independent of the Brownian motion. It's the position of the first green point in the picture that I had before on the blackboard. And Dynkin also says that we know the distribution of this g theta, which turns out to be a gamma distribution. So if we go now to this formal definition, if we combine Dynkin's results with our underlying picture of Brownian motion, then the upshot in the end is very simple. All this theory, ethos theory of excursions, and all the facts about Poisson processes tell us a very simple story. And the story is that if you multiply the maximum of a Brownian bridge and the minimum of the Brownian bridge by square root of an independent gamma random variable, this is equal in law to the maximum of Brownian motion up to g theta and the minimum of Brownian motion up to g theta, right? So this big theory in the end boils out to this very simple fact that you get two random variables that have this distribution here. But we know that the maximum and minimum of this distribution here are the maximum and minimum of a Poisson process, at least conditionally on the local time. And if you have a Poisson process on the real line, it's fairly easy to compute the distribution of the maximum, right? So if I try to draw a little picture, like if you have a Poisson process that has a higher and higher density towards the origin, now I'm not talking about the undergraduate Poisson process anymore, but the Poisson process with a different intensity, then if you want to know that the maximal point of the Poisson process is not bigger than x, this is equal to the probability that here you get 0 points. And that's very simple, right? If you have a Poisson process on a real line with some intensity, and if you have some conditions on that intensity, then it's very easy to compute the distribution of the maximum, because you just use the usual properties of the Poisson processes to do that. Okay, let's now continue. What you can do is that you get an application of the elementary reflection principle And this is, you can derive the positive maximum of a Brownian bridge very easily. It's a simple distribution. You can write down the distribution function of this random variable explicitly, and it's all very simple. So you just use the reflection principle, which again, if you have Brownian motion in any of your undergraduate courses, it all starts with the reflection principle. Is one of the topics that you see, and this is no more than a straightforward application of the one-sided maximum. But what we know now that if we multiply this random variable by the square root of the of this g theta, we get this maximum. But this maximum, again, you can use this result, and the facts about Poisson process is that conditionally on the local time, the maximum of this Brownian motion is the maximum of a Poisson process. So if you look at this side, all the points, the maximum, all the heights of excursions are smaller than x. If you have 0 excursions that are higher than x, it's the pictures that we have here, had here in the corner before. And this very much looks like a Poisson processes. And I just used the intensity. I just used the intensity of the heights of excursions. And I know that the heights of those excursions are a Poisson process. And I know that that Poisson process has a intensity measure that I denote by m bar here. And because I know this one-sided maximum, I can compute m bar. And here it is. It takes some integration. You have to use big books that give you complicated integrals. In this case, I used Gratstein and Rizek, and I computed this intensity measure. And now let's return to the picture again. And I will show you the same pictures again. The idea, again, is this one. You take the Brownian bridge. It's a stochastic process. It's Brownian motion conditioned to be 0 at 1. And it has excursions, which means when the Brownian bridge is away from 0 for a while, you can break these excursions into pieces, just as we had before. And you can look at the height of every excursions, and then you can measure time in such a way that you know at what local time the excursion occurred. And then if you draw the heights of all these excursions, which means I drew the heights of these excursions as these blue points, the excursions occur at some given times and they have a given height. And what I know is this, if I just do it for the Brownian motion, for the Brownian bridge, this is not a Poisson process, and I can't use little ideas like marking and computing the maximum easily, because it isn't a Poisson process. But you can turn it into a Poisson process by doing this. You take the Brownian bridge, you rescale it, which means that you stretch it so that it's not on the interval from 0 to 1, but on the interval from 0 to square root of g theta. And then you also stretch it in the space dimension. And if you do that right, and if you then condition on the local time at the end, you get a Poisson process. And here is the connection. So if you do that and look at the excursions of the stretched, of the rescaled, we call this random rescaling, because you take a random variable and stretch the Brownian bridge to random length. It's not a fixed length like usual Brownian scaling, but it's random rescaling. It's also called random rescaling. And then if you condition it right, the heights of excursions are a Poisson process. And now once you're there, and once you know the intensity of that Poisson process, you can do all the calculations. And here are some calculations that we can now do. For example, the Kolmogorov-Smirnov test is based on this maximum of the absolute value of the Brownian bridge. So it's just one possibility. It's not the only one. And what we now gain from all the theory of the Poisson processes is because conditioned on L, it's a Poisson process. You know that conditionally on L, this is the probability that the excursion is unmarked. This is the probability that the excursion is smaller than X. And then you uncondition it, which means that you just have to integrate over L. And it turns out that you get the hyperbolic tangent of this quantity here. So if you multiply, so the bottom line now, we used a very complicated theory to say this, that if you multiply the Kolmogorov-Smirnov statistics by square root of an independent gamma random variable with parameters 1/2 and theta, then the new random variable has an explicit distribution, which is this one here. It has to do with the hyperbolic tangent. But if you write this left side as an integral, you will find that this is a Laplace transform. So if you denote the distribution function of the Kolmogorov-Smirnov statistic by Fm, what this means, what I had before, in terms of an integral, you now notice that this is actually a Laplace transform, because in the end you have e to the power of minus theta s. And this is a function of s that depends on x, but it's you compute the Laplace transform of this function in the variable s. But now the question is, can you invert this? Yes, of course you can invert. It's not even all that difficult, because you can expand this tangent into an infinite series, and then you invert individual terms of this infinite series. So inverting this Laplace transform, even if you don't have big books that list all possible Laplace transform, you can do it by hand very easily by expanding this tangent into an infinite series and computing it. It doesn't take very much to do that. And then we have derived the famous Kolmogorov-Smirnov statistic, which tells you the asymptotic distribution of the Kolmogorov-Smirnov statistics when n goes to infinity. But this is just one thing that you can gain from this. It is, you can do other things, like you can compute, for example, instead of the maximum, you can take a linear combination of the maximum or the minimum, right? So who says that positive deviations in the Kolmogorov-Smirnov statistics are more important than are equally important than negative deviations? You may have reasons not to do that, but this idea with Poisson processes allows you to play with it. You can give different weights to the positive and negative parts, and it allows you to compute many other things. Here are a few examples. And all of them can be cranked out easily using this idea of rescaling and Poisson processes. So if you multiply, for example, the minimum, you get this expression. So you multiply the minimum by the square root of an independent gamma distributed random variable, you get this expression. This usually comes under the heading of Kuiper's statistics. And you get this. You can compute the distribution of the difference. You may choose to use the difference as your statistics. And all these are closed form expressions. So the magic is that when you multiply by the square root of g theta, you get closed form expressions. If you don't have this g theta here, you have no closed form expressions. You just have infinite series. Once you multiply it by g theta, you convert everything to closed form expressions. And again, all these closed form expressions, as terrible as they may seem, they actually can be inverted. You can do the same for Brownian areas, for example, because the area is again a function of an excursion. If I give you an excursion, you can take the area under that excursion as your statistic. And again, you can do the same thing with rescaling. We did that with Professor Wellner a few years ago. And then you get interesting expressions like this one. You can compute the law of the integral of the positive part of Brownian motion and relate it to the positive area. If we look at the picture, what we're interested in is the sum of all the positive areas and the Brownian bridge. Here I have already rescaled it. And if you rescale it, then this area multiplied by an independent gamma random variable to the power of 3/2 has the same distribution as the integral of the positive Brownian motion up to g theta. So again, we have, and these two are independent. And again, you can relate, then you can relate the Laplace transforms, and you get, I'm close to the end. So Feynman-Katz gives you this, and then you can use this known result that's been around for many years. This is the Airy function. It's one of the special functions. You can recycle this result for the absolute value of the Brownian bridge, absolute value of Brownian motion or Brownian bridge to, and get nice Laplace expressions for Laplace transforms. In this case, they cannot be easily inverted, but at least you have done some work. And again, you can use the areas as your test statistics rather than the absolute deviations or the maxima of the absolute value. You can use linear combinations. I'm close to the end of my lecture, so I'm going very fast. But these ideas about thinning and marking Poisson processes are remarkably powerful ideas. They let you derive many different things, and there are other ramifications. These ideas then developed into papers with my colleagues from Zagreb, Croatia, and there are other papers by John Wellner and myself, and they're all based on this simple idea of marking Poisson processes, but marking very abstract Poisson processes. But the idea is the same. Like if you mark a simple Poisson process on the line, or if you mark a Poisson process in an abstract space, that's the same thing. And there are other connections that have to do with spectrally positive Levy processes, but I believe I will stop here because I believe I'm out of time.
Okay, thank you a lot. Thanks a lot for this, I would say, great lecture. I open the floor to questions. We will extend this for at least 5 minutes. Please just. I will begin with one of mine. So, as you mentioned at the end, the extension to, say, spectrally positive Levy processes and other things that you mentioned. How extendable, basically you use the general Brownian motion, then rescaled and so on. How extendable it is, say, for example, to different types of Brownian motion, like fractional Brownian motion, geometric Brownian motion, mixed fractional. So people at the conference, I think, on Thursday will present on this. Can this be extended, for example, to any type here, or also to Levy processes and so on?
I can tell you that it can be extended to skewed Brownian motion. About fractional Brownian motion, I'm not sure. I would have to look into that. But I would assume that if you find the right rescaling, you can turn into a Poisson process because it's so closely related to Brownian motion that one would expect that in one way or another you can do that.
And would you always end up with closed formulas for the distributions?
Yeah, you mostly wind up with closed formulas. In many cases, they can be inverted, but there are a few cases where that is difficult. So you don't always win, but at least you have a Laplace transform of a distribution, which means that you can compute the moments, and you have the moments, you can approximate the distributions. So the answer in a nutshell is you can't always invert them, but there are very many cases when you can.
Fantastic. Okay, I hope for the questions from others to this. Thank you.
I see one in the chat.
Yes, true. Do the results you have given on the real line hold, again, in a more abstract setting, say on a Hilbert space? BM on a Hilbert space.
Yeah, on a Hilbert space, it's more difficult because you have to reinvent the concept of an excursion away from zero. And even if you take a much simpler case like Brownian motion in the plane, it doesn't return to zero. So what are then excursions, right? You have to reinvent that in some way or another. There are versions of turning the excursions, from example, if you look at the excursion of two-dimensional Brownian motion from a circle, they are a Poisson process if you measure the time right, if you invent the local time, but the calculations are not as elegant, right? Because you know that they are Poisson processes, but it's difficult to compute the intensity. And there are no nice expressions for the intensity. You just theoretically know that it's a Poisson process, but you can't do much with it because there are no elegant formulas for intensities. So that's why it works in one dimension so well, because the intensity measure of the Poisson process that you are looking at is simple and explicit.
Thank you. I hope this answers the questions by Shikica. And Martina has another question. Please, Martina, just unmute.
Yeah, first of all, thank you very much for an amazing lecture. And maybe this doesn't make a lot of sense from like the practical point of view, but is there anything done for different point processes? So like not considering Poisson, but maybe Cox processes or
yeah, what we used here is in fact we reduced the heights of the excursions to a Cox process because we only got to Poisson processes once we conditioned on local time. So if you don't condition, you get a Cox process. So if you have a Cox process to compute the maximum and minimum or the joint distribution of the two, is again easy. So for Cox processes, it works. For more general point processes, it depends, right? How you describe them, how did you describe their distribution?
I give the word now to Tobias. I hope, Martina, this was replied.
Yeah, thank you.
Thanks. Tobias, please.
Again, thank you for the talk. I hope you can hear me. So I just have this small technical question. So these excursions are very important for this theory or this idea. So how do these excursions look close to zero? Because the Brownian motion will attain the value zero very many times right in the beginning. So how will this look? Does that make sense?
Yeah, it's not just the beginning. Every time the Brownian returns to zero, you have the same story. So in the end, what you get is that the small excursions will actually be, in a sense, dense, right? So you get a dense set of very small excursions, and then every now and then you get a longer one. So you get a Poisson process that has infinitely many points. But if you limit yourself to the excursions that have length above epsilon, then you get only finitely many of them.
Okay.
But it's right, like you will get infinitely many very small excursions.
Okay, but this is not a problem. So this.
No, because even on the real line, you can have an intensity that integrates to infinity, right? And if it integrates to infinity, then you know that you will have infinitely many points. But it's still a Poisson process.